Hey there, everybody. In this video, we're going to talk about the method of reduction of order. So it turns out that sometimes when you have a differential equation, say it's a second-order differential equation, you can reduce it down to a first-order differential equation. So by making a change, you can essentially get rid of one of the derivatives. So you can take it from second order to first order, or maybe from third to second, or from fourth to third. And when you reduce the order of a differential equation, it usually will become a little bit easier to solve. So what we'll do in this video is we'll look at this idea of reduction of order, and then we will look at an example where we can put this to use. Okay, so let's take a look. Reduction of order. So consider this differential equation here. Y double prime minus y prime equals 0. Very simple differential equation. It's second order. But what we can do here is we can make a change of variables that will reduce the order. So if I just let z equal y prime, well then, z prime is y double prime. Okay? So I can replace the y double prime here with z prime, and the y prime with z, and what I have now gotten here is a first order differential equation, which I can solve, right? So let's go ahead and solve this. Go ahead and take a moment, figure this out on your own, all right? Pause the video. All right, so when you did that, you should have seen that from your skills that you've learned in solving first order differential equations, it wasn't too hard to come up with z equals some constant of times e to the x. All right, now we can pull that back and get the answer for y, right? Because y prime is equal to z. All right, so we know that y prime is equal to c e to the x. And so by anti-differentiating this, we can get our final solution for y. There we go. Let's just write it like this. C e to the x plus b for some constants c and b. Now, why did this work? Why were we able to reduce the order? Well, notice that it wouldn't have worked if we had a y up here, right? Because we wouldn't have been able to get rid of that y. It would have been stuck down here. Maybe you could write it with an integral symbol or something, but that's not going to be a useful equation for us. So it is because there were no y's appeared, we were able to reduce the order down. All right. If no y's and y primes appeared, we probably could have reduced it down 2 notches. All right, down to taken 2 derivatives off. So that's what you're going to be looking for. So if you ever see that, try letting a new variable z in this case equal y prime, seeing if you can reduce the order down to a first order differential equation. Okay, let's take a look at an example where we can use this. Okay, so the differential equation I want to look at is, there we go, kind of a messy guy there. Okay, so I'm going to give you something for free in this problem. Okay, I want you to notice that e to the x is a solution to the complementary equation. It's a complementary solution. Okay, so either you're going to be given this, or you're going to have, through some skills that you've learned, you're going to be able to figure out what the solutions to the complementary equation are. And we've been doing a lot of this. But I'm just going to point that out to you. Okay, so we have a solution to the complementary equation. So what do if we want to get a solution to the full equation? Well, you should be very used to this by now. It should be no surprise that what we're going to do is we're going to multiply this complementary solution by a function. Okay, so what we're going to do is we're going to consider y equals some function times the complementary solution, u times e to the x. And see if, when we do that, if we can find the function u that will make this a solution to the full differential equation that we started with. Okay? Well, how do we do that? Well, we need to substitute this in up here, so we need to compute 1 and 2 derivatives of what we have. So if we do that, you'll see that y prime is this, and y double prime is this. Okay? Okay, so now we're going to take this stuff and substitute it in up here. Okay, so we go ahead and do that. Okay, so we plug it all in. Now you do a little simplification. So on your own, pause the video, simplify this out, okay? And you should have gotten, so pause, welcome back. You should have gotten this thing reducing down to x u double prime minus u prime e to the x equals x squared. So there's a little bit of, there's some work to get there. Not too much. It's simple algebra, just looking at things and realizing when you're going through here, realizing that e to the x solves this differential equation might help you get there, right? Because when you see this stuff appear, you know that's all going to be 0. But it might just also just cancel out using algebra. So it's a little bit quicker if you use this, but I think just the algebra will also get that stuff to cancel out. So now what do we have here? Well, this looks like what we talked about at the beginning. We've got u double prime and a u prime. I don't see any u's, so this is something we can use reduction of order on, right? So what I'm going to do is I'm going to say let z equal u prime. This will reduce this to a first order differential equation. Okay? Okay, well if z equals u prime, then z prime equals u double prime. So substitute in z. What do we get? We get this. Now we have a first order differential equation. All right, so we're going to solve this first order differential equation to get our answer. Let's arrange terms here. Actually, you know what you should do? You should pause the video, go ahead and solve this. This is something that you should be able to do at this point. So pause the video, solve this, and we'll compare our answers. Okay? Okay, 3, 2, 1. Here's what I would have done. Multiply both sides by e to the minus x, right? So I would have gotten, oh, and then maybe divided through by x. Probably would have done that. So I think we're going to get this. All right, you should have gotten to here. All right, I caught a little mistake here. This, when I divided through by x, I forgot to cancel out the x here, so that should not be there, that little exponent. Okay, so we're going to keep going with this. Now, how do we solve this differential equation? Well, the same way we were doing this first differential equation that this came from, you solve the complementary equation first. Okay, so consider the complementary equation. I'm going to put a z1 in place of z. All right, because that's what we like to call our complementary solution, to keep it separate from our general solution, right? So let's put a 0 on the right-hand side. Go ahead and solve this. Pause the video. Get a solution to this. I'm not going to go through the steps here, but you should see this differential equation is separable. Okay, so you can separate terms and anti-differentiate to find the solution. You'll see that this is a solution. z1 equals x. Now, yes, any multiple of this is also a solution, so you may have gotten c times x. However, we only need any solutions. We don't need the most general solution for this method, okay? This is variation of parameters that we're doing, and if you recall, you can leave out the constant here. So what do we do next? Well, we are going to multiply this by a function, just like we did at the beginning of this problem. We were using variation parameters. We're doing it again. We're doing the whole process again. Usually we multiply by u, but we already used the letter u for something else, so this time we're going to use a different letter. Let's use v. All right, it's next to u in the alphabet, so that sounds good to me. So what I'm going to do is consider z. We're going to hope that our general solution up here can be written as some function v times x. And if that's the case, then z prime is going to be expressible as follows, right? So we're going to substitute that back in there, okay? So let's see what we get. Now z over x is just going to be v, okay? And it should be no surprise to you that these things cancel off. When this method works, that's what happens, right? Okay, so what do we have now? Well, we have this differential equation. I can divide both sides by x. And I see that v prime is equal to e to the minus x. Well, this is easy to solve, right? V is the antiderivative of this. It's a negative e to the minus x plus a constant, right? Okay, we basically are finished. We just have to unwind everything, all right? We solved all the differential equations. We just have to unwind everything. So where was v being used? Well, v was the function we were multiplying by x to get z, okay? So now we know what z is, right? Z is this thing times x. Okay, but what was z? Well, if we recall, z was u prime. Okay, so that means that u prime is equal to this. Okay, so I lied. There is one more differential equation. We have to resolve this now. Okay, so if u prime is this, what's u? Well, do a little bit of anti-differentiation here, and you'll see that we get this. Okay? Okay, now we got u. Where was u being used? Well, let's look up above. U was the function we were multiplying y1 by to get y, our final answer. Okay, what was y1? Oh, we were given y1 right up here, e to the x. So we're just going to multiply this by u to get y in the end. All right, so that's all we got to do now. Y equals u times y1, right? So we're going to multiply this stuff by e to the x. What do I get? Well, e to the x times e to the minus x is just 1. I'm going to write that as c over 2. Okay, and I'm going to make one more change. This is our final answer, but it's just not good form to write a general constant divided by something usually. Unless you have a good reason for doing that, you shouldn't. I mean, an arbitrary constant divided by a number is still another arbitrary constant. So let's just simplify this one step further by just writing this as follows. Let's just call c over 2, we'll just call that c1. And I'll just call b c2, right? It's just a little bit simpler this way. Why divide by 2 when it's just still just keeps it a constant, right? So this is our final answer. So we used variation of parameters a couple times, but the important step to make note of here is the reduction of order, right? When we noticed that, where did we notice? Oh, down here. We noticed that there were no u's, it was all u primes and double primes. That's where we can reduce it to a lower order differential equation, all right, to get to our answer. And then it's using the methods that we learned over and over again until we get to the answer, okay? So I hope you learned something there. I'll see you in the next video.